Hey there. In this video, we are going to apply an inverse Laplace transform to a few different functions using the table of Laplace transforms. Okay, and so I've got the table of formulas here of what I get from taking the inverse Laplace of some really common functions, and we're going to use those to evaluate each one of these functions here. So the first one, I want to find the inverse Laplace of 3 over s cubed minus 48 over s to the fifth. Whenever you have more than one term, you can always split this up into a couple of different Laplace transforms. So I could say rewrite this as the Laplace inverse of 3 over s cubed minus the Laplace inverse of 48 over s to the fifth, and then I can deal with them each separately. Now, both of these are a constant over a power of s, and so that looks like our second formula over here from the inverse Laplace table, where I have n factorial over s to the n plus 1, and if I take the inverse Laplace of that, I get t to the n. So looking at the first one, if I have an exponent of 3 on the s, then that means that n is 1 less than that. It's going to be 2. And that means that I need a 2 factorial in the numerator. So I'm going to take this 3 and throw it out front. And then I'm going to add a 2 factorial to the top where that 3 was. And now I've fundamentally changed things, so I need to undo what I just did. 2 factorial is just 2. So if I also divide by 2, since I just multiplied by 2, that will undo it, and I have something that's equal to what I started with. Okay, so now I have 3 halves times the Laplace inverse of 2 factorial over 3 to the s. And I'm just going to finish this one off before I move to that second term. So this would be 3 halves times t to the 2. So t squared is what I get for that first one. For the second one, I have an s to the fifth in the denominator, which means that n is 4. And that means that I need a 4 factorial in the numerator. So I'm going to figure out what goes out front in a second. But I need a 4 factorial out front to make this work. And with 4 factorial, that's 4 times 3 times 2 times 1. So that's 12 times 2 gives me 24. Now, 48 happens to be 2 times 24. So if I just put a 2 out front, then I've broken up the 48 into 2 times 4 factorial, or 2 times 24. And that one now I can evaluate, and I get minus 2t to the fourth. Okay, so that's how you can kind of play around with the numerator to get it to line up with one of the formulas from the table. On this next one, I'm trying to take the inverse Laplace of 4s over 4s squared plus 1. And just like last time, I'm going to go to my table and see which one of these is the one I want to use, and then what do I need to do to manipulate this expression to get it to look more like that. So this one looks an awful lot like our cosine. Here, where I have s over s squared plus k squared. There's an extra 4 on top and an extra 4 in front of the s squared, though. So I do need to factor those out of my expression here. So I'm going to pull the 4 out from the numerator, and I'm also going to pull the 4 out from the denominator. So I have a 4 over 4, or 1, out front. And now inside left is an s on the top. And if I factor a 4, I have to factor out of both terms in the denominator. So 4s squared plus 1 is going to become s squared plus 1/4, since 4 times 1/4 would give me the 1 that was there originally. Okay, so now it looks just like it. And in this case, k is whatever is being squared in the denominator there. So 1/2 squared would give me 1/4. So this should be equal to 1 out front times cosine of 1/2 t, or t over 2. Okay, and the last one here, I have 1 over s squared plus 3s, and I want to find the inverse Laplace. Now, this one is different from the others because I have a denominator that is factorable. It's a constant over something with an s squared. So I'm looking at this and thinking of the sine function. But I'm going to start by factoring the denominator. Whenever you have multiple factors or a quadratic that is factorable in the denominator, we're going to want to factor that first. So I can factor an s out. I get 1 over s times s plus 3. Now, seeing this, I'm no longer really thinking about that sine function. And what I'm going to need to do is I need to break this down in two separate fractions. So I can do this one just like I did the first one. And that means I have to do a partial fraction decomposition. Now I'm going to cheat here. I'm not going to do the partial fraction decomposition. I'm just going to show you what you would get. But on a test, you would have to actually do all the steps for the partial fraction decomposition. So it turns out if I decompose this into 1 over, or something over s plus something over s plus 3, I would get a 1/3 over 1 over s, or over s. I'm going to write this as 1/3 times the Laplace inverse of 1 over s. And then for the other numerator, I would get a negative 1/3. So I'm going to put that one out in front of the Laplace inverse. And so this is minus 1/3 Laplace inverse of 1 over s plus 3. And now that it's broken down, I can see this isn't going to give me trig functions. The first one is going to be just like our first example, where I have a constant over a power of s. And the second one is this e to the at function here. So those are the two that I'm going to use. On the first one, n is 0. And I end up this is actually just the first one, isn't it? Because there's no power on the s. So 1 over s is just 1. So this is just 1/3 minus 1/3. And then the Laplace of 1 over s plus 3 is going to be e to the negative 3t, where a is negative 3. And that is how you can use a table to evaluate the inverse Laplace of a function.